Hello everyone, my name is Bruna Coldebella. I'm a PhD student at Université Laval with Professors Christophe Flame, Georges Bedouin and Carlos Guillemette research group. And today I'm going to present some results of my PhD, dive a little bit into the isotopic characterization of the pyrite to pyrrhotite desulfidation reaction across the different metamorphic zones in the Pontiac Subprovince. So we talk a lot about orogenic gold deposits and the source, and I just wanted to quickly point it out that with mostly unknown fluid pathways and different processes that can occur at or near the depositional sites, such as fluid mixing or fluid rock interaction, the chemical composition of the fluid is going to very likely be obscure or change, so it's very hard to trace back what is the exact characteristics of the metal and ligand in the ligand sources. So this is what we are trying to discuss here today. We do know that orogenic gold fluids are aquocarbonics with some content of NaCl, and gold is mainly transported as hydrogen sulfur complexes, and the fluids are stable at near neutral pH in a wide range of temperature and pressure. And so gold is deposited by this destabilization of these molecules, of these gold hydrogen sulfur molecules. And one thing that is very important for us is that the abundance of these molecules is directly connected to the sulfur content in the fluid. Diogo and Isaac talked a little bit about this, but it is thought that some studies show that gold originally hosted in sedimentary pyrite is released to the fluid during the pyrite to pyrrhotite transition in Barrovian or prograde metamorphism, so between 375 to 575 degrees Celsius. So when the pyrite breaks down to the pyrrhotite, it releases sulfur and possibly gold and other metals to the fluid. And this is just some models proposed by Tompkins, in which we can see a range of temperature and a range of pressure in which sulfur can be released to the fluid, so a sulfur window, and it's a much wider window in a pyrrolitic composition in comparison to a mafic rock composition, for example. So we took advantage of the great work done by Isaac in mapping the isogrades in the Pontiac south of Rouyn-Noranda, and we chose some of his samples, either by samples that he modeled or samples that we could see a good relationship between pyrite and pyrrhotite, to try to, the metapyrites and the metawakis, to try to better understand the pyrite to pyrrhotite transition across the different metamorphic grades. So starting at the biotite zone, we already see the transition. So like Diogo said, we see pyrite 1 occurring with pyrrhotite, a later generation of pyrite that we call pyrite 2, chalcopyrite associated, and the flames of pentlandite and the pyrrhotite. At the garnet zone, we also see this corroded pyrite 1 reacting with pyrrhotite, but pyrrhotite is already the main sulfide, followed by pyrite 1, second generation of pyrite, pyrite 2, chalcopyrite, and pentlandite flames. And sometimes we see the pyrite 2 overgrowing pyrite 1 in some of these reactions. At starolite zone, pyrite 2 becomes more common than pyrite 1, so you can see that pyrite 1 slowly decreases as you increase the metamorphic grade. And we can see here preserved in a kind of a core in being recrystallized to pyrite 2 and pyrrhotite associated. And like Isaac said, unfortunately we don't have samples from the kyanite zone, but at sillimanite zone you don't have occurrence of pyrite 1 anymore. It's just pyrrhotite, pyrite 2, chalcopyrite, and pentlandite flames. So we see this systematic decrease in pyrite and increase of pyrrhotite as you go from north to south, increasing metamorphic grade from the biotite zone to the sillimanite zone. Now, like Diogo said, one very good tool that we can use to trace back sources and changes in the fluids is the multiple sulfur isotopes, and specifically for us, the mass-independent fractionation of sulfur. Because if you see here at this graph on the left, we have age at the x-axis and the Cap33 sulfur signature at the y-axis. And the Cap33 sulfur signature represents the mass-independent fractionation of sulfur. And we can see here measures of sedimentary rocks. And after the great oxygenation event, you don't have the signature anymore, so Cap33 is always equal 0. And if we take a look very quickly at the sulfur cycle, starting at the sub-atmospheric subcycle, we see that sulfur is photodissociated by ultraviolet radiation between two different channels, either becoming reduced species with a positive Cap33 sulfur or oxidized species with a negative Cap33 sulfur species. So you're going to have, as sulfur goes through the different rocks in the different reservoirs, it's going to have different signatures. So for example, oceanic sulfate is going to have negative Cap33 sulfur signature, and sedimentary pyrite from elemental sulfur is going to have a positive Cap33 sulfur signature. And recent works by Laflamme and collaborators 2018 also noticed a positive Cap33 sulfur signature in orogenic gold deposits that indicates that sulfur in these deposits has been at least partially sourced in a sedimentary reservoir. In terms of the pyrite to pyrrhotite transition and sulfur isotopes, there is experimental work that has been done by Liu and collaborators 2020, in which they transformed pyrrhotite from a pyrite, initial pyrite, and they measure these results after. So they have increasing delta 34 sulfur values from pyrite to pyrrhotite and a positive Cap33 sulfur signature preserved during the desulfidation. So for our results, we analyzed in situ in SIMS at the University of Western Australia, both pyrite 1, pyrrhotite, some analysis of chalcopyrite and pyrite 2, and we separated here by the different metamorphic zones, so biotite zone, garnet zone, and starlight zone. And so we see a variation of Cap33 between negative 0.3 to all the way to positive 0.7, 0.8. And delta 34 delta 34 sulfur minus 1 to almost 5 per mil. And we see here in the Cap36 sulfur and the Cap33 sulfur space that our samples, when you go to the squares, that is pyrite, to the circles, that is pyrrhotite, the reaction follows the mass-dependent fractionation. So the metamorphism is not influencing the signature. If we quickly compare to Canadian Malartic, this is a work by Hout and collaborators 2014. They've done sulfur isotopes in some of the host rocks, so you can see gray wackies in a white square in the Pontiac Group. They also see the same positive Cap33 sulfur signature. And if we compare to Herzog and collaborators 2024, we see the same positive delta 34 signature, some positive Cap33 signatures here, but it's mostly negative. But for us, what was really important was to analyze, to try to trace and analyze the reaction, so within the texture of pyrite to pyrrhotite. And we saw pretty similar results to the experimental work presented by Liu and collaborators in 2020, where we have a mostly increasing delta 34 sulfur and a mostly conserved Cap33 sulfur signature. These are examples from the biotite zone and the garnet zone. So we see a shift in the delta 34 sulfur of -1 plus minus 0.9 per mil, and in the Cap33 sulfur signature, a shift of 0.06 plus minus 0.17 per mil. And that's okay according to the analytical error. So there's a negligible sulfur isotope fractionation between the pyrite one and the produced pyrrhotite. And with no significant changes in the fluid, we also see no significant changes in the fluid oxidation condition. It's very likely that the H2S produced by the desulfidation reaction will have the same sulfur signature as the pyrite from the source, so the pyrite one in our case. The Cap33 sulfur signature from the desulfidized pyrite to pyrrhotite is preserved and represents a traceable reservoir of sulfur in Archean metasedimentary rocks. And this is important because some deposits are in a higher metamorphic grade, so you're going to have only pyrrhotite. All the pyrite, the sedimentary pyrite or the source pyrite is going to be consumed by the pyrrhotite. So if you analyze this pyrrhotite for Cap33 sulfur signature, it's going to be the same from the source because it's preserved. So to conclude, the concurrence of the formation, the metamorphism, and the fluid generation with the desulfidation reaction can portray an optimal gold fluid window, enabling the mobilization of H2S in aurific-bearing fluids. That's it for today. Thank you.